Today, we're diving into a substance that sounds like it's straight out of science fiction, but it is absolutely real: antimatter. And it just might hold the key to one of the most powerful secrets in the entire universe. You see, antimatter represents a way to unlock just incredible amounts of energy. When it comes into contact with regular matter, it releases that energy with nearly 100% efficiency. I mean, it's a process that makes nuclear fusion look like a tiny little campfire. But here's the catch, the central tension of this whole story. This unbelievable power source is also the most difficult, most resource-hungry substance we have ever tried to make. And that right there, that contradiction, is what makes antimatter so fascinating. So where did this wild idea even come from? Well, it wasn't from looking through a telescope or a microscope. Nope, it came from a piece of paper. The story of antimatter begins as a kind of ghost lurking inside an equation, a mathematical quirk that nobody was looking for. It all starts right here in 1928. A physicist named Paul Dirac is working on an equation, and it keeps giving him this really bizarre answer. For 4 whole years, it's just a ghost in the math. But then, in 1932, an experimental physicist, Carl Anderson, actually finds it in the real world, proving Dirac's math was spot on all along. So, what was this famous equation? Well, Dirac was trying to do something huge, create a single formula for the electron that brought together the 2 biggest ideas in modern physics: quantum mechanics and Einstein's special relativity. And he did it. But his beautiful equation had a very strange side effect. Okay, to get what was so weird about it, let's use a super simple analogy. Imagine someone asks you to solve this equation: x squared equals 4. So what number, when you multiply it by itself, gives you 4? Now, your first thought is probably 2. And you're right. But that's not the only answer, is it? Because -2 times -2 also equals 4. Dirac's equation was just like that. One solution was perfect. It described the electron we all know and love, but there was this other solution, this negative version, and nobody had a clue what it was. And that is exactly what Carl Anderson found 4 years later. That negative solution wasn't just a quirk in the math. It was a real physical particle. It had the exact same mass as an electron, but it had the opposite charge, a positive charge. He had discovered the anti-electron, which we now call the positron, the very first piece of antimatter ever found. And it turns out the positron wasn't some lonely freak of nature. Its discovery basically opened the floodgates. It revealed an entire shadow family of particles, a whole zoo of cosmic twins. The rule is actually pretty simple. For every particle of matter you can think of, there's an antimatter twin that has the opposite electrical charge. So our negatively charged electron has a positively charged twin, the positron, and the positively charged proton has a negatively charged twin, the antiproton. And this mirror image thing is almost perfect. Even particles with no charge, like a neutron, have an antimatter twin, the antineutron. How? Well, their insides, the quarks, have charges that are flipped in the anti-version. And then you get some really weird cases, like the photon, the particle of light, which is actually its own antiparticle. Now here's where it gets really mind-bending. You can actually build stuff with these antiparticles. If you take an antiproton and get a positron to orbit it, guess what you get? You get an atom of antihydrogen. Scientists at CERN actually did this for the first time back in 1995, proving that antimatter isn't just loose particles, it can form atoms, just like the regular matter all around us. So if you can build things with it, why isn't there any antihydrogen just floating around? That brings us to antimatter's most famous and most violent feature: what happens when these 2 mirror image worlds, matter and antimatter, finally come together. It's a beautifully simple process, but incredibly powerful. When a particle of matter touches its antimatter twin, their opposite properties, like their electrical charge, just cancel each other out. They completely vanish, they annihilate, and their entire combined mass is converted into a burst of pure energy. So just how much energy are we talking about here? Well, get this. The energy you'd get from annihilating just a single gram of antimatter would be enough to launch a CERN engineer to the International Space Station not just once, but 30 or 40 times, from 1 gram. And the reason it's so powerful all comes down to efficiency. Nuclear fusion, right, the process that powers our sun, that only converts about 1% of its mass into energy. Annihilation is nearly 100% efficient. It is, hands down, the most efficient energy conversion process that we know of in all of physics. Okay, so it's ridiculously powerful. So why aren't we using antimatter to power our cities? Well, to answer that, let's take a little trip to the antimatter factory at CERN and see the brutal reality of trying to make and hold on to this stuff. Here is the biggest problem. In physics, there's no such thing as a free lunch. Annihilation is just E equals mc squared working perfectly, turning mass into energy. But to make antimatter, you have to run that equation backwards. You have to turn a truly colossal amount of energy into a teeny tiny bit of mass. In fact, it takes billions of times more energy to create it than you could ever hope to get back. As a power source, it's a total bust. And even if you manage to make a little bit, trying to store it is a complete nightmare. You can't let it touch anything, so it has to be trapped in a perfect vacuum, held in place by powerful magnetic fields. Our current records are pretty incredible feats of engineering. The base experiment held a single antiproton for 614 days, and the alpha experiment has trapped whole antihydrogen atoms for about 100 hours. These are amazing achievements, but they're a long, long way from being practical. And just to put all of this into perspective, if you wanted to produce just 1 gram of antihydrogen, at the speed we can make it right now at CERN, it would take you billions of years. That is way, way longer than the universe has even existed. All of this difficulty leads us to the final and maybe the most profound question of all. If it's so incredibly hard for us to make antimatter, why did the universe bother making it in the first place? And if it did, where did it all go? You see, according to our best theories, the Big Bang should have created matter and antimatter in perfect, equal amounts. For every single quark, there should have been an antiquark. For every electron, a positron. But when we look out at the universe, that's just not what we see. Everything we can see, from the smallest speck of dust to the biggest galaxy, it's all made of matter. If there were giant galaxies made of antimatter out there, we'd see these huge flares of energy where they meet regular galaxies. But we see nothing like that. The anti-stuff is just gone. And that leaves us right here. Why is there something instead of nothing? How is it that matter won the cosmic war against its twin? Figuring this out isn't just some academic curiosity. It's one of the biggest unsolved puzzles in all of physics. It's a hunt for the tiny flaw in the laws of nature that allowed us and our entire universe to exist at all.